Okay, good afternoon and good morning and good evening. So welcome to the 56th ASE seminar, Advanced Supercomputing Environment. So before starting this seminar, I just briefly go through the history of this meeting. So we started this seminar, 2008. And so this seminar is held irregularly. So when we have domestic or international visitors to the Information Technology Center in University of Tokyo. Okay. And the official language is not fixed, but today it's English. Okay. And the first seminar was on March 3rd, 2008. Okay. So it covers a wide range of topics. So any topics related to HPC and supercomputing. And the last meeting before COVID-19 was hold this on February 4th, 2020. And we have one online meeting during the COVID era. And we restarted this series of meetings 2 years ago. So after that, we have been doing this hybrid time seminar. Okay, so the title of this seminar today is the integration of the simulation, data, learning, and beyond, part 2. So why part 2? So actually, we did part 1 2 years ago. So it's a closing symposium of my former project, H3 of video. So I talk about this later. Okay. Okay, so this is a program at that time, and we have 2 invited speakers at that time. Okay. Okay, so today's agenda is like this. We have a talk by Professor Tanbui Tang from University of Texas, and we have 2 talks from our center. Okay, so let me introduce our today's keynote speakers, guest speakers, Professor Tanbui Tang. So he's a professor, actually, so from this September. Okay. So congratulations.
Yeah, thank you.
So professor of the University of Texas, Department of the Aerospace Engineering and Engineering Mechanics. And he's also the Oden Institute for Functional Engineering Sciences at the University of Tokyo. And he's a co-director, Center for Scientific Machine Learning at the Oden Institute. So he's originally from Vietnam.
Yeah.
Okay. And his PhD is from MIT in the astronautics and aeronautics in 2007. And he joined the University of Texas since 2013, I remember. So yeah, he got many awards, but I'd like to emphasize he's one of the Golden Bell finalists. Yeah. So this is a list of his interests. So it also covers a wide range, starting with the quantum science and some machine learning and uncertainty quantification and numerical analysis. And I believe you are originally from the CFD.
Yeah. That's right.
Okay. Okay. So please join me to welcome our keynote speaker today.
Thank you. Want to reshare? Right. Yeah. Okay, so thank you, Kengo, for the opportunity to share with all of you online and in person here on about my research. So like he said, I work over the years as a CFD model reduction, and then I spent about a decade on doing inverse problem, Bayesian optimization inverse problem, right, with PD constraints. And then for the past 8 or 9 years, I working on scientific machine learning. It's how to combine, scientific computation like we do, right, and machine learning, so that we have a better machine learning method, right? Instead of just data-driven, can we actually use what we know about how to solve equation? For example, finite element method, finite volume methods, to actually make the machine learning method more reliable, right, more accurate. And that's what I'm going to share with you today. So these are, and we recently really interested in a digital twin. Because that's actually the important thing. I'm going to share with you what I mean by digital twin later. but let me introduce you my student here, Hai, and then Jiawei is from Taiwan. That's where I met Kenyo. And then Thomas is from US. Okay, so let me to tell you what you mean by digital twins, right? So there are many people talking about digital twins, and they may mean different things. So at least I want to show you what I mean by digital twins, so that we understand each other's. Okay, so on the left, as you can see here, are physical assets, like for example, car, humans, right? Could be an engine, and it's all could be a hurricane or a storm. Okay, so these what we mean by physical twin. And us, right, as a mathematician, engineer, what do we want to do? Or a human in general, what do we want to do? We want to understand these so that we can make prediction, right? That's only what we want to do. We want to get more knowledge about the physical phenomena and want to understand so that we know what's going to happen, right? We can do that so that we can improve our life, our technologies. So if you do so, right, if you do the and that requires domain knowledge or mathematical modeling. It could be scientific machine learning. It could be anything, right? You don't, for models that you have mathematical models, right? Governing equation, then you just do the usual approach, mathematical modeling. But actually, there are many situations where you don't, right? So you can do whatever you want, including machine learning. Then you come up with a curve, right? When we have a governing equation that we typically do here, the supercomputing centers, you have equations, right? You discretize, right? When you want, after you discretize, you implement it on the computers, okay? And then you can, hope to forecast something. And this is the traditional simulation. It's not a digital twin, that's what I mean, right? I'm gonna tell you, digital twin is much more than that. Okay, so let me repeat I'll emphasize the important here. This is traditional simulation. When you come from physical phenomena, you come up with the mathematical models, discretize, implement your algorithm on the computers, and then try to forecast something, right? Try to predict something, right? That is traditional simulation. So the problem with the traditional simulation is the following. When we have a physical phenomena here, you come up with a governing equation, right? Or mathematical models. That is the best that you can do, right? There's no reason why our mathematical model is actually as close as possible to the real, right? There's only a discrepancy between our mathematical model and the reality, which is the physical twin. And now that mathematical model, you do discretization or you do approximation. You introduce further uncertainty and approximation, or you introduce further inadequacy model in your simulation code here. And more importantly, even that, right? What are the boundary conditions? What are the initial conditions? What are the parameters? If you do fluid flow, what are the random numbers, right? There's so many things that you don't know. If you are on the fly, right? I think all of us actually fly one way for another's, or even the train, especially the fly, when they go to the wind gust or turbulent, right? The boundary conditions change, right? And in very random manners, you never know. So typically, the problem with traditional simulation is that you have to assume the parameter, like random numbers. You have to assume the boundary condition, initial condition, and hopefully you can solve and then try to see, whether it's actually physically correct or match the reality. Okay, but that's not a digital twin. So digital twin involve a couple of things. First, how do you improve your model? How do you actually improve your inadequacy model to be close to a physical twin? How do I know boundary condition? How do I know the differences between how do I improve the gap between our digital model and the reality, right? You take the data, you take the real data from the physical models. And what do? You calibrate, right? Or you do inverse problem. You saw these are the same words. Or you do data assimilation. I know that a lot of people in this center do weather forecast and climate, right? So data assimilation, inverse problem, and parameter calibration, they have a similar nature. Okay, so basically you want to calibrate your parameters. The parameters could be initial condition, boundary condition, or the actual parameters. So these are the similar thing. You calibrate so that your inadequate model as close be close to the physical phenomena, and then you may forecast again, right? But we want to go beyond that. If we want to go beyond that, for example, if I want during the running, if I want to change my posture running so that I maximize my energy burn, right? Or I'm in the real car racing right now, right? What should I, of course, we actually use on the car racer, right? They just based on their experience and then the speed. But if you want to do like what is that? If I given the road, we given the condition, but the wind and people around me, what is the optimized speed? What is optimal speed, right? What should I turn to actually win the race? So this require an optimization and control, and for this one, you may do by experiment, right? But it's better that if you can do so on a digital model, right? Because otherwise, especially this one is actually impossible to optimize or control. The hurricane, you cannot control the hurricane, right? You cannot optimize. The problem here is that where should I put the sensors to maximize our information about the storm? Right? In order to do that, you have to solve optimization. Actually, in fact, it's called optimal experimental design. If you solve that optimization to figure out where to put the sensor so that I know more about the hurricane, so that I know how to evacuate people, right? So that's required, definitely you have to solve on the digital twins. Right? In general, it's too expensive or it's impossible to do on the physical twin. You have to do in digital twins. And after you do that, what do? You make a decision. That means you put the sensors and you change your poster or you change the way that you control the car, right? And when you change the physical twin, it generates a new data. The new data allow you to update your digital model, right? And your digital model allow you to do optimization, right? Parameter calibration, optimization control, and so on and so forth. You make decision to put back to the digital physical model, and this loop again and again, right? In the dynamical manner, tight closed loops, right? So that's what we mean by digital twin. Digital twin include traditional simulation as a part of that, right? But it's also, we need to do both calibration and the own optimization and decision making. Now, the problem with the traditional model, this is HBC Center here, traditional approach, he mentioned about Gordon Bell thing, right? So you try to do as fast as possible to run as big as possible computer traditional method. The traditional method is nice, beautiful, right? It's accurate and it's physics based. But the problem is take time, right? For example, if I want to do hurricane, I want to check the storm all here. I want to do in real time, then it will not work, right? Real time decision making, real time optimization, real time inverse problem, right? Or real time forecast, it may be difficult. Okay, so that's where we actually, the machine learning is a way to help to speed up, right? So that is exactly what I'm going to talk about in this talk. All right. So I'm not going to talk about all these, but I just want to let you know, take the opportunity to let you know what I'm doing in my group, right? So my group actually have about 12 PhD students work on various aspects of deep learning techniques for real-time digital twins. But the work that I'm going to show you today, which is the three here, were done by the student that I just showed. But the other work done by the other student. But let me tell you a couple of things here. If you do deep learning, how many of us here are doing deep learning, machine learning? Most, yeah. So if you do so, right, then the first question for me when I started doing research on deep learning, the question is, as a traditional applied mathematician or scientific computation people, right? How do you know it work well, right? So, and if you look at the literatures, there's so many different neural network activation function or different architecture. You have different proof of why such a neural network is going to approximate any function well. But then they are very technical and they are very different from each other. Okay, so in this work, what we did is actually we come up with a very unified constructive framework that actually all of us could understand, right? Traditional scientific computation people can understand, and one theorem, right? Or for the multiple theorem that works for all neural networks, right? So it's easier. So it's just for fun theoretically, right? And the second question in neural network or deep learning is the following: how many layers, right? In your deep learning model, how many neurons on each layer? How do you know? So if you only do, and you said that everybody does a lot of tuning, right? Like hand manual tuning, it takes a lot of times, and if you are lucky enough, you pick the right architectures, right? So and of course, there's a Bayesian optimization approach out there, but it's very expensive. Okay, my question for our group or myself is that can we use traditional method, right? Traditional applied math method to actually do it, right? To do the architecture design so that we have a more principled way and more rigorous way of doing architecture design, right? If you find element method, find a difference, find a volume, you know that there's one important techniques, mesh adaptivity, right? For me, how many layers? This is just time adaptivity. How many neurons? It's just a spatial adaptivity, right? Can we use a posteriori error analysis or similar approach for mesh adaptivity to do that for neural network? And yes, we did. So we have that work, and this is almost done. And another thing that we do in our group is that when you look at the architecture design, it's very similar to topology optimization. So as I mentioned, you can go here. My collaborator in Osaka University, he did topology optimization, right? So when you look at how many layers that you add, how many more neurons you add and remove, right? It's a topology optimization problem. So we actually, we borrow the technique from topology optimization and use it, right, to do architecture design. So it's more meaningful and more rigorous, right? Okay, so the third one that I'm going to talk about is the forward. And I'm also talk about English as well. But basically what I'm going to talk about is how to do forecast, real-time forecast here, this part, okay? I'm going to talk more about that later. But the other thing that we do in the group is also calibrations. Calibration here, this calibrations of the parameter. When you have observation data, can I do calibration or solve an English problem in real time, right? That's what we want. And we also do control. So this is with uncertainty quantifications. If you do deep learning, you also know, right? After you train, you test, but then you know that you're going to make error in your prediction. How do you quantify the uncertainty or the error in your neural network or machine learning techniques? So this is where we actually use our expertise in Bayesian approach to do it in more mathematical manners. Okay, so I'm going to skip talking about this, but I'm going to introduce you a little bit on our DT framework, our digital twin framework as well. So I'm going to focus on this, and then if we have time, I'm going to talk a little bit about this. Okay. Okay, these are the student that I just showed you that actually work on this topics and a little bit of this. Okay. Okay, so I'm going to look at a generic equation here, right? Mathematical model here, such as a time-dependent PDEs. So the right-hand side on a spatial derivative, and then the left-hand side is a time derivative, and it could be very nonlinear. Okay, so what we do in the traditional, he talk about CFD. In the CFD community, typically what we do is that we discretize the right-hand side here with some, like for example, finite element method, right? So you have a spatial derivative, you do finite element, finite volume, finite difference, spectral method, whatever you are in love with, right? Then you discretize the spatials, and then you have a system of ODE. This should be the total derivative. I'm sorry about that, right? So you have a system of ODE, and then you can do any time integrations that you want. So our idea is this, right? Can we learn? Actually, let me, before we talk about idea, let me tell you what are the two major schools there in the scientific machine learning for solving PDEs. The first group is saying this: don't forget about your PDEs. Forget about your mathematical knowledge about PDEs. Give me the data. Right? I only work on data, so it's completely data driven. And then the second school say that, okay, give me the equation, but forget about all of your discretization techniques, all of your mathematical method. Give me the equations, and then I'm trying to develop a solution for that equations, right? But my approach is different. My approach falls into the third category, which is actually not popular there. Can we actually develop a machine learning method, the technique to learn the way we solve PDEs, right? For example, can we learn finite element methods? The reason I said so is that I'm going to show you later. I'm interested in hyperbolic conservation law, which are very difficult, right? If you just use the first two approaches, it does not work, right? On the other hand, from mathematical or computational applied math, over the year we developed, well-defined, approaches for this hyperbolic conservation law. we should learn that approach instead of throw away our knowledge, okay? So the question, our approach is, can we learn the discretization, whatever discretization that you come up with here, spatials? Because after you learn this, then you can solve the system of ODEs, right? Easily. Okay, so that is the idea. I'm gonna put down a neural network that learn the discretizations, F here, okay? So this is where the difference that you can see as well. The neural network, our neural network is not a solution. The neural network is a discretization because it takes the solution vectors, right, and return the discretization. Okay, so that's the key point. Suppose that you learn this already, your discretization already, then you can solve this explicit, implicit the way you want, right, as usual. Okay, so the idea is very simple, overall idea. So how we actually do that? Of course, how do we train this? How do we train this? So the beauty of this approach is that we only learn spatial, right? And then the time discretization, you can do whatever you don't do later after you train. Okay, so how do you train? Okay, so in order for training, we do discretization for training only, right? For training only. On the left-hand side here, remember this is spatial discretizations. And if I just do for simplicity, right? I'm gonna show you forward Euler. So this is our code, our algorithms. This is the neural network solution. Remember, this is a neural network, and U-tutor is the neural network solution. So this you can think about as, right? This is nothing more is considered as the neural network or machine learning code, and this is your numerical code. Okay, so the first thing we want is that, okay, we want the machine learning solution code need to match the solution from our discretizations when training. So this is the first part, the loss function, right? Machine learning solution match the solution from our discretization. That's the first part of the loss function. And then we want more, right? And this is where this is where it is important. We want the solution from the machine learning code. When it's substituted into the discretized code, it should satisfy, right? So you see that if I substitute U-tutor in here, and I divide delta t, I get this. And we want this. And then if you manipulate a little bit, change a little bit, you get two terms, right? The first term is still U-tutor, the machine learning solution. And this one is U-bar. U-bar is the substitution of the machine learning solution into the numerical code, okay? And of course, we want them to be equal for the machine learning solution to satisfy the discretization. Unfortunately, this is not possible, right? So instead, we're going to minimize the difference, right, between the machine learning solution and its substitution into the numerical code. So this is the second term. This is the second term. Okay, so this U-tutor minus U-bar is our second term here, and you have alpha here, the regularization. You can see that the bigger alpha, the more that we want this machine learning solution to satisfy our discretization. Okay. Now that's the first ingredient. Two term in our loss. This second ingredient is very important, and it's kind of counterintuitive. So remember that we use these two train, right? Solution from the numerical method to train. We add noise into it. So this is randomization technique, right? We don't use the original data. We add noise into it. So we randomize to get V. So the log function is now V, right? Instead of U, because we work on the noisy data. And that's what we call randomized loss here. LRAN is a randomized loss. This is a traditional loss. Why should we do so? Right? Why does it actually help? Let me show you the result here, right? A theorem. So you show that you can show that on average, the randomized loss is the same as the original loss plus regularization term. Well, this is interesting, right? So delta, what is delta? So delta is the noise, the variance of the noise, the variance of this noise. Okay. So the larger the variance of the noise, right, the more that you would like to regularize your solution. And remember, this is implicit. This is only theoretically, right? So adding noise on average is the same as the original loss plus regularizations. So, and what's up to the second order, okay? So forget about second order term here. So there are four terms here. So you see that P1, P2 come from this first data-driven loss. This is what we call data-driven. This is what we call model constraint because we constrain our discretization here. So P1, P2 come from this. Q1, Q2 come from the this term. Remember this term, we want the neural network solution to satisfy the discretizations. Okay, so let me show you these two terms, P1 and Q1. So what P1 does? So P1 is a trace of identity plus delta t, and this is Jacobian of your neural network. Okay, so this is actually an H1 norm, right? If you do inverse problem, right, or you do regularization techniques, this actually, because it is a part of the loss function, right? And you know, notice that this is the derivative of the neural network, or the Jacobian of the neural network. So active noise is the same as making sure that the neural network actually behaves, because the derivative cannot be big, right? Because you're gonna minimize the randomized loss. We're gonna minimize this. When you minimize this, you minimize the original loss plus this one, right? So this one cannot be big. So the neural network must be well behaved, must be well behaving. Okay, and then let's do Q1. Remember that Q1 is from the model constraint term, or the discretization constraint term. And notice that this is F, this is the gradient of F minus gradient of phi. Remember that phi is trying to be as close as possible to F, which is already in the loss function. When you randomize it implicitly, right, the randomization also for the first derivative, or the Jacobian of the neural network, and your discretization to be the same, right? In fact, it's also the second derivative. So this is the interesting part, right? Implicitly, when you add noise, you induce implicit regularization, and regularization makes things better. Why? If you think about a traditional interpolation, right? You want phi to be the same as F at the training point, but when you add noise, not only phi and matching the F, but also the derivative, right? And this, if you relate it to what we know about interpolation, Lagrange interpolation, only yield function values. But Hermit interpolation also yield derivative, and Hermit is much more accurate, right? So if you recall what we learned about interpolations. So that's the beauty of randomization. It's a kind of, you know, induce a Hermit interpolations, right? Or forcing the similarity. And more importantly, right? I'm going to show you the results on error analysis as well. But I'm going to show you a little bit again intuition here, right? The red are the training points. When you randomize your training point, right? You basically improve the coverage. This is intuition, right? This is a mathematical statement. But it's the intuition, another way to look at the way we do. Intuitively, when you add noise, you enlarge the data space, right? The black point is a test data. If you don't randomize, then predicting data, the black point may be difficult, right? But if you randomize it, when you cover the region that you haven't seen, but this is generality. Remember that when you do machine learning, the key question is generalization. And we're going to show you our method generalize way beyond that the other method can do, right? So remember, right, two. This is one intuition, and this is what we just showed. Not only is force the function value, or it forced the neural network to be close at the discretization, but it's also the derivative to be close, right? All right, so another beauty of that approach is that now you can characterize the error between your neural network solution and the numerical solution. Okay, so the error, you can show that epsilon I, this is the at the comma Tn, right? Is bounded above by two terms, G and F. F is the difference between F and phi, which when you do minimization, they are close, right? And interestingly, if you look at G have the first derivative differences and the neural network behavior. So the beauty is that when you do randomization, these two are under control, right? That they are under control. This one also under control. Therefore, you can control your error, right? And therefore, you expect that your method actually have the stability and accuracy, which I'm going to show you. Okay. Any questions so far? Okay. I got none. Then let me go directly to the numerical results. Okay. So the first problem that we're looking at is a Berger equation, viscous Berger equation with nu as a viscosity. So what we are interested in is to predict the solution at new initial condition, okay? And we want the prediction solution that on in time. And look at this figure. This figure have a lot of information here. First, the blue, vertical blue, what is it here? We generate the data from 0 to 100 time step, right, to do training. But our question is that can we predict beyond, way beyond that, right? So that's the question that we ask. Okay, so there are a lot of curves here. The first curve is the data-driven, the square. This is the data-driven approach. Without the second loss, remember that my loss function have two terms, right? The first is the data-driven. The second one is a discretization constraint. So the pure machine learning means that it does not have a second term, right? No discretization constraint. So you see that this is unseen data, by the way. This is unseen cases where I generate a new 500 new initial conditions. And this is the average error, right, in time. And remember that this is training period. And you see that the machine learning actually does quite well inside the training period, okay? So if you are not believing much about deep learning in particular, right, or machine learning, this actually is not bad, right? If you have data, then machine learning model can actually learn pretty good. However, it's slow, right? As it cannot generalize beyond. Now, if you increase to 600 data, this is 200 data, right? So, and then the solid green square is with 600 data, same method, only data driven. It's actually better. It's actually better. So more data. The second message is that more data, deep learning can be better. Okay. Now we're gonna talk about our two methods. Our method, right, with the same data, 200 and 600. Our method, remember, the difference is that we add the second discretization constraint term, the circle here, and you see that the circle here is almost the same as the solid green. Remember, the solid green have 600 data. Our approach here only 200 data. So the first message is that if you incorporate your knowledge about discretization, then you may need much less amount of data. You see that 200 versus 600, and yet you still get a similar accuracy. Okay, so that's the first message. Now I increase this to 600 data. Our approach have two terms. Remember that, right? 600 data is almost the same as the numerical curve, by the way, right? So the purple solid curve is a numerical curve compared to the error, right? Or compared to the solution. So you see that incorporating the discretization in your training, right, or discretization, then not only you get better results with less data, but also you have the stability. You see the long-term accuracy and stability that, you know, purely machine learning would not have it, right? Or data-driven would not have it, and way beyond that what you're training. Okay, the next question that we try to answer is the variability. If you do deep learning, you know, right? For each initialization of your weight and biases, you do training, you get one solution. You do a new initialization, you train, you get a new solution. Okay, so then which one that I should do, right? Because same code that if you train with a different initial initialization for weight and biases, I do differently, right? Different initialization. I will same code, nothing changed, but you're gonna get different. Here, as you can see here, I'm gonna took that 32 random initialization of weight and biases, right? And I generate 32 neural network solutions. And this is again the blue thing here is only the first term, data-driven, purely data-driven. You see that not only is unstable, but it's also have a huge variability. Okay, so your solution will be a bit different than mine, right? The only reason is that we use different initializations. Now, if we use our approach, remember our approach alpha, the regularization, right? Discretization, regularization constraint term. If we have that, then we use the same case. Then you see that not only is stable, right? That is I already show you in the last slide, but also the variability is very small, and this is important because why? It basically say that it does not matter. That you do your initialization the way you want or I do. If we use the same code, we get similar results, almost the same. Right? This is really important. Okay, so I'm gonna I'm gonna skip the this one. This is for noise, but I'm gonna skip this one because we may run out of time. So the next approach is the discontinuous looking DigiNet approach, right? It's same approach that I just told you. The current approach actually had a problem. It cannot capture the spatial correlations, and then more importantly, what we did that I just showed you, we use one just feed forward neural network, right? It will we tried out. It didn't work for shock problems, so we have to design a new approach. Okay, so what is the new approach? Again, stick with our knowledge about discretizations. So what this is just for fun, right? It's just for fun. This is, by the way, UT logo, UT University of Texas Austin logo. Okay, so anyways, the black triangles are the mesh, right? And then you know that for each mesh, you have a dual mesh. So the orange one is a dual mesh. We're gonna put down graph neural network on the dual mesh. So each of the vertex here is a vertex of our graph neural network. Okay. And then so we're gonna take out this piece. So this piece, I'm gonna take it out here. So this is our vertex of our neural network, our graph neural network. It represents the elements. Okay. And then on the edge represent the flux, the communication with your neighbors. Okay, so in the graph neural network, if you are familiar, then we need to do two things. We need to learn two things, right? Edge aggregation and the volume or the vertex aggregations. So this is perfect for numerical method for fluid flow problem, right? Because that in fluid flow, what we do upwind type, right? We update the numerical flux. We use the neighbor information, update the numerical flux on each of the edge, right? And then we update the volumes. So based on that, we see the similarity. We immediately match the graph neural network and the discontinuous Galerkin, which is a finite element method. So what? So we do the same way. We do the same way. We want to learn the right hand side. Remember that we do exactly the same way. The discretization is what we learn, but this is only for training. For shock problem, we need more strong stability preserving discretization for training only, right? And remember, this is the right hand side discretization, and this is our neural network that we want to learn the discretizations. And how does the neural network look like? I think I just mentioned to you, but I'm going to do it again here, right? A little bit more concrete. This is at the element K or the vertex K of my graph neural network, and this is the solution from the neighbors. So what do? When you have a solution from the neighbors, you compute the information at the battery, right? And traditionally, you're going to compute numerical flux. What we do is that actually we put down neural network here. This is edge aggregations. The feed flux is to learn the numerical flux or to learn the Riemann solvers, okay? And then the solution of your elements go through a different path. And there's a volume neural network here. It's actually do over integration. It learn over integration to update your element solutions. And then these two together, right? Come back, add and back to get the phi DGNet here. Okay, so same way, but now this approach tied strongly to the underlying discretization, and therefore it's going to be generalized very well, which I'm going to show you now. Okay, I'm going to show you first the L4 problem. This is thinking about the wind of the aircraft. We cut in a cross sections. It looked like that. Okay, the fluid flow going to go from left to right here. And this is the Euler equation, compressible Euler equations. Well, what are the training data here? Mach number 0.8. That means the flow is 0.8 times of the speed of sound. And we choose two gas constant, 1.2, 1.6, for training. And the angle attack, right? Angle attack of the wind and the flow. So this is the angle. If you are not familiar with aerodynamics, this is 3 degrees. And then the time is 0 to 1.2. Okay. So we have only two cases. Two training data in a sense, right? Now we're going to test with a completely different Mach number, 1.2, much higher Mach number, and then gamma, the gas constant 1.4, and different angle attack, more nonlinear and longer time. So that's what we want to do, okay? And I'm going to tell you this is if you do traditional method, right? Whatever method out there is going to be difficult. I'm going to tell you why our method does perform well. So this is the DG solutions, and this is our DGNet for the unseen K. Now remember the unseen K is this, 1.2, 1.4, and different angle attack and longer time. And this is the DG solution. This is our solution. That you see that at first, I mean, of course, I'm going to show you the really the numbers, right? Not only just eyeball norm, but also number in a second. But on the left-hand side, you're going to see the two curve. This one without randomization, same method without randomization, and the method with randomization 4%. It's much better, with more accurate and more stable, right? Remember that it match our proof, right? Okay. Another case is the double Mach repression. Remember, this is a shock, unseen case as well. This is a DG solution. This is our DGNet solution. It's almost invisible, right? With the difference between the two. And remember that we learn the right-hand side. We learn the discretization. You see that we also compute the discretization, the right-hand side, to see if there's any difference. And you, again, visibly, you don't see it. We're going to show the number in a second. Now, this is a hypersonic case, right? Mach number is 17, 17 faster than the speed of sound, unseen case as well. DG on the left, and I'm sorry, yeah, and DGNet, our approach on the right. Again, you cannot see it, but I'm going to show you numbers. So just show you that the differences between the two. Now, let me actually see that I can share you the, okay, here. So this is, there are many cases that we look at, right? So this is a case, for example, you can see, this is the geometry that we train, okay? And this is a sharp, you see on the structure here, this is the DG solution, our solution. But we're gonna predict to a new geometry. I mean, I'm showing, you know, different regime already, but this is a different geometry, new geometry that we haven't seen. New structure as well. So this is the DG solution, this is our solutions. Okay, so this sounds that too good to be true that our approach is actually generalized very well, right? So is that like too good to be true? But I'm going to explain to you why it actually is not surprise. Now, actually, how do I get back to my stop share? Okay, and then share again the this one. So why can't we have such a generality, right? With, you know, traditional approach would be difficult. Remember that we learned discretizations. If you have the numerical code, you change when you write it, right? When you wrote your numerical code, you change the initial condition, you change the boundary condition, you change the mesh, you change the geometry, the same code working. And because we learned the code, so that's why I can generalize wells, right? It behaves exactly the numerical code, and this is actually another view to look at it. Okay, because we have online people. Okay, so this table is important. We have 5 cases, right? With different problem, different geometry as well. Okay, different geometry, different problem, but the same compressible Euler equations. The diagonal is the new network solution that use, for example, for this one, right? We use forward facing. I just showed you the forward facing problem. Maybe the L4, maybe look at the L4 so that we know better. For the L4 problem, we use the L4 data and train a new network, right? And then predict unseen cases. And this is the error that you get. Now, the interesting is that you use the new network that train with L4 data, you predict with the other cases. This is generality that you can see. It's actually not too bad. It's not too bad, right? So diagonally, you train with the same problem. You predict the same problem with just different setting, right? But off diagonal, you train on one problem, you predict the rest, right? And you see that the error is actually typically, you know, like 1-digit accuracy, which is very nice, right? Of course, the diagonal, you have 2-digit accuracy. So that's the beauty of this approach. Okay, now training time for all these cases. You see very little training time here. The reason is that when we do a graph neural network, you have even one simulation, you have a lot of data, right? So the training is actually not too bad, right? And this is if you use the DG for prediction, this is prediction, and the explicit DG. If you do explicit method, typically it's hard to beat, right? And you do supercomputing center here, if you do explicit method, typically it's really hard to beat explicit method. And the message here is that the DGNet approach that we do, even it's beat the explicit method, not much, right? 5 times faster, 4, 8 times, 3 times, depend on the problems. And we are working on making it much faster than that, right? But the key thing is that explicit method that we would think that our method would not beat, but it does. Not only you have accurate, but also you have the speed. Okay, so if you have that, you can do uncertainty quantification. Let me skip that. Okay, so let me summarize my idea here so that we can stop. So the idea is very simple, right? It's very simple. You have a discretization in space. We want to design a new network to learn that discretization. So we need two techniques, right? Discretization, constraint, loss, and randomization. Without this, it would not really work, okay? And the digital twin thing, maybe I don't have much time, but I'm gonna show you how we actually do that for tracking and tracking vehicle. Okay, very quick here. Okay, so we have two vehicle could attack three different targets here. Okay, so initially we only have data here. So initially each vehicle can attack each of the target equally. For example, the vehicle one can attack this target with 31%, 33%, so on and so forth. One here is for vehicle one, this is for vehicle two. So we fast forward real-time forecast to how it's gonna go, the optimal path. And now we let the simulation, or now this is where we get more data, right? When you get more data, you update, right? And then you predict again. And you see that we do on real time and right to do both simulation and calibration that I showed you before. Now you actually predict, oh, unlikely that the first vehicle is going to attack it, but it more likely attack the two target. And as time go on, we get more data. And you see that at this moment, we are already quite certain that the first vehicle going to attack the first target with 98%, right, of certainty. Okay, so let me stop. I am here. That so that we can maybe have questions. Not sure whether we have any time left. So again, this is the key thing that we want. We talk here is a way to hopefully to share you information about what we do on digital twin, right? To do be able to do fast forecast and inverse problem calibrations, and how we do that learn the traditional methods instead of throwing them away. Thank you.
Okay, thank you very much. Nice talk. Are there any questions? Yes.
I don't see any questions. So we have 35 people online, but I don't see any questions there. So it's okay.
Okay.
Oh. Yeah, please.
Okay, so I have the question about the biological differentials case. So you use the 600 data for training, but it is possible to improve the accuracy if you use more than using the data more than 600 data.
Yeah, that's right. Yes, you can. But yeah, that's a.
Right.
Yeah, but depend. For example, here it's almost impossible. Why? That's a very good question, by the way. A great question. Very good, right? So the question is, so for the people online, right? The question is, remember that I showed you 600 data, or our approach is here, almost the same numerical method, right? So the question is, if I increase way more than 600 data, can I get better? And the answer is actually no. Why? Because remember that we decided the method to learn the numerical. So this is the numerical method, right? So our approach is at most accurate as the numerical method. It cannot go beyond that because we designed to learn it, right? So that's a good question. It's not better. It can be only similar. Yeah. Thank you. Yes, please.
How about some device of computing resource for running the other method?
Running the
computing resource.
Oh yeah. That's a good question. Actually, yeah, I didn't have the actual here. Okay, so yeah, I didn't have I need to get that information for you. So the question is for the online people, the question is how many GPU that we use. I don't have that information. I only had the type of the GPU that we use. Yeah, in tech, so the beauty is like this here. Tech, we have the largest supercomputing center, among on the university. So we have a lot of GPU. I just forgot how many GPU that my student used to train. Right, I'm sorry. I just don't have that at my mind right now.
In your field.
Say again.
How still missing. Better the other method or more.
Oh, yeah. So if in the same field, if, by the way, that's a good question as well. So is our method better than the existing method? Okay, let me say it this way, right? Let me say it this way. First, hyperbolic conservation law with shocks. If you go around, not many work there, a couple, right? Only a couple of papers on that. And they don't generalize well, right? Because they do the first two approach, data-driven or using only equations. They don't generalize well. If you use the new, map number, especially, it will not be able to do new geometry. And the beauty, by the way, this is also a good question. We train only once, we don't retrain. If you use pin approach, right, physics and for new network, you
So capturing the shock wave.
Mm.
So did you apply any special treatment for that?
Yeah, so that's the good question. So the question is that, how could we learn the capture the shock waves? Okay, that's a good question. Let me go back to here. Remember that if you do DG, what does DG do? So all finite volume upwind method, any upwind finite volume, finite difference, or finite elements. What do? This is the current time step, right? If you are starting time step right now, you get information from your neighbor. So this is you. You get information from neighbor and your information. You compute the numerical flux here, and then you update your elements, right? That's the DG approach or any upwind approach. So we design our graph neural network exactly that, right? This is the vertex upper our graph, and this is the edge. Remember, this is a vertex our graph neural network. This is the edge, and along the edge here we have a neural network that learn the Riemann solvers. Okay, so and in order to capture the shock, you need to be conservative, right? Especially you need to be able to solve the Riemann problem. Is that right? So we design our approach to learn the Riemann solver here, right? So that's here. So we get information from our neighbor and ourselves. The flux here actually learn the Riemann solvers. So F star is the numerical flux, upwind flux. So that's why it's actually can capture the shock because it's conservative, right? In the sense that to the accuracy of the neural network, right? And that's why it can capture, right? For any hyperbolic conservation law, for you to capture the shock, you need to be conservative, right? And also we do have a slope limiting.
Do you have any plan to extend your idea to Navier-Stokes?
Yeah, actually, right now we're working on that right now tonight. So we want to do 3 days, right? We want to do 3 days. This is only 2 days. We want to do compressible Navier-Stokes and 3 days on complex geometry like aircraft was. Yeah.
Okay, so any other questions or
See.
network?
Yeah, I don't see any question online. Okay, that's good. Okay. Yes,
Okay,
please.
so you're showing that I think you trained the model for the specific target specific program, right? So
Yeah.
So do you have the plan to generalize that program to the target for the various arbitrary geometry, for example?
Geometry, yeah, this is actually.
Yeah, this one. So I think that you trained the data for the specific program. Right?
The specific.
Can you try to generalize that for the generalized mesh and program?
Okay, so the question is that we train for a specific problem. Okay, so or can it be generalized to more cases? Okay, so first, our approach only works for compressible Euler equations, right? But it doesn't matter which geometry, because if you look at this, right? If you look at this, yeah, because remember that we actually know here where you see that on the geometry different, right? Different geometry here, and remember that we show you the result here. We train on one problem, we solve the other problem. So geometry in the condition mesh is not a problem. But if you change the equation, right? You change the compressible Euler to Navier-Stokes, then you have to retrain it. Yeah. Okay, but your question is very important because right now we also look at our group. We look at foundational model for scientific computing, right? Can we actually train a model that works for add many equation as much as possible, right? Not only geometry, not only mesh, but also equations. So that's ongoing. Yeah, that's an important question.
So, remote question?
I don't see any question here on the chat. Do we? Well, I don't see on my side. Yeah, there is no question on the chat.
May I have a question?
Okay, go ahead.
Yeah, please go ahead.
Okay, thank you. Very interesting talk. I'm Sia Nisida from Riken. You added the perturbation to the training data to minimize the difference in the Jacobian, right? So I'm curious about how did you generate the random perturbation? I mean that the individual perturbation has their own growth rate. So I guess the more unstable perturbation may result in the more efficient training in terms of the epoch count or accuracy. Do you have any comment on that?
Yeah, actually, that's a good question, right? So let me repeat the question. How do we, of course, how do you see that? We see that there's an implicit regularization, right, based on the Jacobian here. And how does let me repeat your question, but may not be entirely correct, right? It's how do we use the randomization, right? What is the randomization that we use, and how does it change from one epoch to another epoch? Okay, so let me answer the question in two parts, right? The first part is that I just want to emphasize on the Jacobian here, right? I mean, on the Jacobian here that you see is actually implicit. We never compute the Jacobian, never, right? Because this is just theory. By adding what we do, minimize this. We add the noise into the data, and we just minimize this. This theoretical result just say that when you add random noise, it's implicitly make the Jacobian to be the same, right? And Hessian to be the same. Okay, so that's the first message that I just want to confirm. Now, how do we add noise, right? This is actually a good question because it leads me to the second figure that I didn't talk about, right? Remember that we add noise epsilon. Now, how do we add noise? First, what we do is that each epoch we generate noise. For each epoch we generate noise, and then we train a little bit, and then with new epoch we generate new noise. So same from the same distribution, right? Epsilon come from the same distribution. The way we do so, if we do that, then we don't need to save on the data, right? That's the beauty. And the secondly, if you can see here, the question is that if we can, our method is actually how much our method is sensible to the noise that we add, right? Because when you add random noise epsilon, it's just a random sample, right? Just one random sample. How do we know good? Okay, so here you see our approach. This is just data-driven. Again, the data-driven approach have a lot strong, variability. But our approach basically said that it doesn't matter, what random sample that you give me, right? If you give me a random sample from the same distribution, my result and your result are similar. Okay, so hopefully I answer part of your question. Does it answer the question?
Yeah. Okay, thank you very much.
Thank you.
Any other questions? Okay, thank you very much.
Thank you.
The next speaker is myself. So, I'll talk about the innovative supercomputing by heterogeneous integrations of simulations data running on large-scale heterogeneous systems. So we have some common idea. So with a digital twin. So my talk is mainly from the viewpoint of the high-performance computing. Okay, so by the way, so I found that Professor Peter Lux passed away last week.
Yeah.
So today I'm very sad, but that's all. I'm very happy to meet my friend. So so I like Lux vendor scheme very much. So it's very nice, very efficient, and also stable and accurate. So I love this so much. Okay. So I have one book written by Peter Lux. Okay, so this is the co-authors and collaborators of this work. So I'd like to thank my sponsors. So I'd like to briefly introduce myself. So actually, so many of you know myself. Okay, so I skipped this part, but so as you may know, so my master's degree is from University of Texas and aerospace engineering. So, and I worked for industry for a long time, but so during that time, so my company supported my so study abroad. After finishing my master's degree, I was hired by TICOM. It's a Texas Institute of the Computational Mechanics, funded by Dr. Oden. So now it's the Oden Institute, so Tan is working for. Okay, so this is a history of my research. And so last 6 months in TICOM, I published 4 papers. So I think so this is one of the most productive days in my life. So I can do that, not do that now. Okay. So after coming up to Japan, so I still working for the CFD, but so mainly switching to the CFD, not CFD, numerical algorithms such as multi-degree or other issues, including QC, HPC, hybrid. Okay, so this is the history of our supercomputer centers. We have so nearly 3,000 users, and more than 55% are from outside of the University of Tokyo. Okay, so we have 2 big systems and a 6-year lifetime. So therefore, every 3 years we have new systems. But you can see we have some gaps here. So mainly because of the delay of the development of the hardware. So sometimes we have 4 systems, but so now we are operating new systems. So you can see we have a new very many systems with the green tags. So it's by GPU or accelerator. So it's getting larger. So integration of the simulation, data, and learning. So we call this the S plus D plus L. So this is our main strategy in recent 10 years. So as you know, supercomputing has been changing, and various types of the workloads for the supercomputers are emerged. So in addition to the traditional computer science and engineering simulations, we have new users and new workloads for the big data analytics, AI, and machine learning. And we thought, so integration of these 3, simulation, data, and learning is very important towards the society 5.0. So this is a human-centered society and a safe and secure proposed by Japanese government. So by integration of the cyberspace and the physical space. So it's a very similar idea to the digital twin. So we call this project BDEC. It's an internal project started 10 years ago. We have been developing a platform for integration of the S plus D plus L. But in our case, we are focusing on simulation. So data and learning are supporting the simulation. So H3 open, so, oops. Yeah, I think I put a long slide and I show you the good one. Just a minute. Okay, so I showed you the long slide. So this is a proper slide. So it describes our systems with Stellar BDX around. So it's on the first floor of this building. So this is the first BDX systems, and operation started 4 years ago. So total peak performance is 33 petaflops, and aggregated memory bandwidth is 8.38 petabyte per second. So it's by Fujitsu. So we have 2 types of node groups. One is a simulation node groups called Odyssey. So it's include nearly 8,000 Fujitsu Prime HPC FX 1000 by A64FX architecture. So it's a commercial version of the Fugaku supercomputer, and the size is 1/20th. So another part is the data and learning node called Aquarius. It's for the data analytics and AI machine learning workload. So it includes 45 nodes of the Intel Xeon Ice Lake and NVIDIA A100. So totally you have 350 so NVIDIA A100 GPUs. So this part connected to the external resources directly. And these two parts are connected through the InfiniBand EDR with a 2 terabyte per sec, and fast file system, 1 terabyte per sec. Okay, so I go back to the original slide. So I'm sorry for convenience. Okay, so this is how we utilize this system. Okay, so we try to optimize the models and the parameters for simulations by support of the data assimilation, data analytics, and machine learning. So then we can accelerate the cycles for the nonlinear simulations for the real world. So this is a research area based on the machine learning, machine hours, last fiscal year until this March. So Odyssey part is mainly used for the very traditional CSE workloads, engineering, earth and space science, material science, and energy and physics. But you can see in the case of the Aquarius, it's a very different color. We still use this system for the engineering, so something like these simulations. But we have a 25% for AI. So mostly they are spent for the experiments for the large language model. And also we have another new color. So this pink part is a bioinformatics. It's by something like genome analysis or medical image recognition by machine learning. So the main users of this area is, so for example, University of Tokyo Hospital. Okay, so this is a most recent top 500. So that will be updated in a couple of weeks. So now the Odyssey part is 58th in the world. Okay. So and fourth in sixth in Japan. So this is the hardware, and we also developed a software. So it's called H3 OpenBDEC. It's an innovative software platform for integration of S+D parcel on this type of the systems. So that was a 5-year project supported by Japanese government. So from 2019 to 2024 March, 1 year ago. Okay. PI myself, and the total budget is 1.4 billion US dollars. Okay. So these are the members, and also the former postdocs, and also contributors. And we have several international collaborators. Okay. Okay, we have 3 innovations. Okay, so one is utilizing the mixed precisions and so low precisions. So second one is combining the machine learning and simulations. So as for the second part, so the next speaker, my colleague, Professor Shimokabe, will talk about that. So here I focus on the software and the utilities for heterogeneous environment, such as Wisteria PDX01. Okay, so actually, Wisteria PDX01 is a really so first really heterogeneous system in the world. Because we have so such kind of the systems in the many supercomputer centers, but they are separated. But our systems can work together, so simultaneously. Okay, so you can see, so we have a different architecture for the GPU and CPU. So therefore, combining these systems by MPI is impossible. But fortunately, it's connected through the network and the fast file system, and we utilize that. So we developed the H3 OpenSys weight IO as a part of the H3 OpenBDEC, which I mentioned in the previous page. So we call this software as a weight IO. So this is a library for interprocess communication over InfiniBand EDR with MPI-like interface. So we utilize a very primitive InfiniBand library. So we have 3 types. One is a weight IO socket through network, and another one is so through the fast file system, and also hybrid is an automatic switching between InfiniBand and fast file systems. So actually, so this is developed by my colleague, Professor Sumimoto, so sitting there. Okay, so this is a sample interface. So yeah, instead of calling MPI functions, we can call weight IO functions. Okay? And so that's we can easily communicate between these 2 different programs. So with IO can be called from Fortran, C, C++, Python, and we are also developing the Julia version.
Is it open? Is it
Not open, but if you are interested, so we can work together. Okay, so I'll show you one of the examples. So it's a integration of the seismic wave propagation simulation and the real-time data observation and assimilation. Okay. And we start with the combination of the assimilation and simulation, and then switch to the pure simulation. So this is the systems. We have a JDXnet. It's an observational network in Japan for the seismic phenomena. So we have more than 2,000 points in Japan, and they can send the data real time, so through network. So our idea is introducing these data and so try to assimilate the solution. Okay. So this Aquarius is receiving the data, and they apply the filtering, and it's sent to the this part Odyssey. So they are doing the simulation and assimilation, and finally, so results are coming back to the Aquarius part, and we do the visualization. Okay. So this is a sample interface. This is corresponding to sending filtered data from Aquarius and receiving that at Odyssey. Okay. So both are written in very classical Fortran language, and instead of calling the MPI ISEN, so they are calling wait IO MPI ISEN many times. So they are just sending. So this part is just receiving. Okay, so this is one of the examples for that type of the programs. So for the of Niigata 2007 earthquake. So this is Niigata. So have you ever been there before? So it's 200 kilometers away from Tokyo. Okay, so we also developed H3 Open Util MP. So MP stands for the multi-physics. So it's a multi-physics coupler originally. It's developed for ocean, atmosphere, or fluid structure interaction. But we extended this coupler for the coupling of the simulation on Odyssey and AI on Aquarius. Okay. So combined with the weight IO library, which I mentioned before. So originally, so it was developed for the MPI functions, but it's extended to this type of combined method. So next page shows a sample of this type of the applications. So it's about the global cloud physics. Okay. So in this type of simulation, we usually combine the high resolution model and the low resolution model. So low resolution model is called parameterization. Okay, and so basically, so they are doing solving the same equations, but I think that as a small part of the physics model is a little bit different, and it's very coarse. And you can see, so 75% is spent for Odyssey, so this high resolution model. So our motivation is replace this parameterization part with AI. Okay, so then we can reduce the time, not so dramatically because it's only 25%. But so we train the this surrogate model using the high resolution model simulations. Okay, and the training and inference got by this GPU part using the PyTorch with a 3-layer perceptron. It's a very simple model. Okay, and the training of the AI by simulation and the simulation plus inferencing it's a seamless on Odyssey and Aquarius. So this is a result comparison of the simulation and AI. So input is air density, internal energy, and vapor density. And we are estimating the gradient in time direction of these 3 parameters. So this center line is a simulations, and this one is a prediction by machine learning. So generally speaking, so they are matching very well. But so we still have a problem for capturing the peaks. We are still improving this part. So another application is also related to the atmosphere and climate type simulations. So in the case of the very typical weather prediction or climate simulations, we apply the ensemble-based data simulation. So in that case, we run the many cases with different parameters. Then we do the simulations and estimate the result. But generally speaking, so that means we need to run a lot of cases, 100 or 1,000. So it's very expensive. So for example, if you do the computations for the 14-kilometer resolution model for the global climate model, we need 160 nodes. Okay, so from the viewpoint of the memory. Okay. So if we do 64 ensemble for 9-hour ensemble-based data simulations, we need more than 2,000 node hours. So actually, so this 9 hours is very small. So therefore, 2,000 node hours is not so big, but yeah, it's still big hours.
They're completely in parallel, right?
Yes, it's embarrassingly parallel. But we propose a new idea, so-called ensemble coupling. So it's an ensemble plus coupling. So basically, we are replacing the ensemble part with a very coarse meshes. And using the technique called the filtered nudging with a very fine mesh. So yeah, we can replace the ensemble simulations with many cases. So we still need one run using the very high resolution, but we can save the computation time. So in this case, we use that resolution of the 224 kilometers instead of 14 kilometers. So it's a very coarse mesh. And by this method, and also we add the capability of the single precision computations, we reduce the computation time from the 2,000 node hours to the less than 20 node hours. So 100% improvement. And the next page shows a comparison between the original data simulation and the ensemble coupling. So you can see, we can keep the accuracy even if we apply the very coarse mesh and this type of the method. But this is a very preliminary data, and we are still going to validate this method. Okay, so another one is a JHPC quantum. And so actually, this weight IO library is very nice, and we can extend this idea to connect any type of CPUs, GPUs, and others, such as AI tips or quantum computers. Okay, so we apply this idea to the QC HPC hybrid computing. So actually, current quantum computer is not so big. So therefore, combining with supercomputers like accelerator is one of the trends. Okay. So JHPC quantum is supported by Japanese government. Started last 2 years ago, November. Okay, and it's a 5-year project. So it's a collaboration among RIKEN, SoftBank, University of Tokyo, and Osaka University. So in this project, we are introducing 2 real quantum computers. So one is the IBM system in Kobe. So it's almost installed. Okay, it's a most recent one with a 156 qubit. It's called Heron system. So another one is the continuum ion trap system. It's a RIKEN Wako. It's just 1 hour from here. Okay, and it's small, but it's more stable, and it's already started operations. Target applications are quantum sciences and also quantum machine learning or machine learning. Okay. So role of the University of Tokyo, the research and development of the system software for this QC HPC hybrid environment. So it's an extension of the HCD OpenVDEC, which I mentioned in the previous part. And the Fugaku at RIKEN and our supercomputers will be connected with QCs in. So now it changed. So connection itself will start this fall to winter. So 3 months before that. Okay, so last fiscal year, because we still BDX is a convenient system for simulating the QC HPC hybrid environment. So we consider this GPU part as a quantum computers and the Odyssey part as a supercomputers. And we tested some of our software. So actually, we installed CUDA-Q. It's a quantum simulator developed by NVIDIA. So it's installed on the Aquarius part. And so we constructed a very simple system for simulating this environment. So actually, we did a one-day tutorial last December. So it's a very nice opportunities for learning this, like this way. Okay. So at that time, we selected a very simple VQE, variational quantum eigensolver as a applications. So the purpose is trying to calculate the ground state, so minimum energy, so which is corresponding to the minimum eigenvalue for the mathematical point of view. And so we have 2 parts for the Aquarius and the Odyssey. So this is a very brief overview of the algorithms. So this is the steps for the VQE, and we have 3 steps. Okay, and the first 2 parts is sampling, and the last part is optimizing the computation. So we need to repeat these 2 parts. And the first part is done by Aquarius, so simulated quantum computers, and the latter part is done by supercomputers. So actually, so it's a very small system. It's just for the hydrogen case. We need just 4 qubit. So therefore, we just use a single node and single GPU. Okay. So this is the structure of the program. Yeah, we are doing the function of the weight IO for the C language and the Python API. Okay. So this is a Python script. So we are calling some weight IO function here. So this is the job script. So it's a very special, and we need to submit the job script separately for GPU part and CPU part. So we have some special rule, and if the jobs are matched, and also the resources are available for both parts, we can run the code. Okay. So this is a demonstration. So you can see after several iterations, it is converging to the solutions. Actually, so Tan and I met 2 years ago in Taiwan. So at the National Taiwan University, we are teaching. Okay, so in the separate lectures, but in some reasons, so we share the office 1 week. So that's the beginning of our interaction. So anyway, so this February we visited Taiwan once, and we made a tutorial about the weight IO library and the coupler, and also we did quantum computing tutorial. It's a very nice experience. More than 30. So probably you remember this group.
Yeah, I remember that.
Okay. Okay, so I have some slides for introducing our new system, which we started operation this January. So it's called Miyabi, and it's operated by University of Tokyo and University of Tsukuba. Okay, and it's a first GPU-centric system of our university. And so this is basically Grace Hopper system, and we have more than 1,000 Grace Hopper super chips. So that is the Miyabi G. And the Miyabi C is a CPU only part. It includes Xeon parts, the Intel Sapphire Rapids. So it's also the heterogeneous architectures. But more than 98% of the computer resources are for this GPU part. And we have a part file system called Super Flash by DD Exascaler. And all nodes are connected through the full section bandwidth through the weekly band. But generally, we operate so these two parts are separated. But we have a weight IO library, so we can easily connect these two parts. Okay, so this is the system. So it's in another campus in Kashiwa. So it's a very nice view. So it's now 28th in the world. So yeah, we have many types of the similar grasshopper system like this. Okay, so yeah, this is a summary, and so I just introduced our system, software, and applications. So including quantum HPC hybrid, and a little bit about our systems. Okay, thank you very much for your attention. Okay, any questions? Okay, go ahead.
Actually, the connection, you call it Wisari, right? Wisari?
Wisteria.
It's very nice because previously when we tried to do a foundational model, we combine PyTorch, right? And FireDrake. You know FireDrake, right? Yeah. But we have an issue. I'm not sure what you have the same issue because FireDrake is a CPU code, but PyTorch is GPU, right? And GPU is typically much faster, and then CPU is much slower. So we need to call the Jacobians from the FireDrake as well. So in the example that you show, when you run on the first system, forgot the name, Odyssey, right? Odyssey. Are they also both on GPU or CPU or only CPU?
Odyssey part is only CPU.
Only CPU. Yeah. So and then do you actually in your method there? What I don't know what the machine learning method that you use for parameterization, right? Remember that? Do you need the Jacobian from the Odyssey code? The code in Odyssey? Only data.
Yeah, only data I feed.
Yeah, but you know that the load balancing is going to be difficult. Right?
Yeah. Yes.
How do you actually make that keep everybody busy? That's actually the challenge. How do you load balancing between Odyssey and Wisteria?
Yeah, it's a good question, and so it's one of the points for this type of computations. So generally speaking, so if we run the code separately, probably we have some idle time. So yeah, in order to avoid that, we need very sophisticated methods such as overlapping the two types of communication or some pipeline type operations. But in this case, we didn't do that type of thing.
Yeah. It's kind of non-traditional, right? Because if you do CPU alone, then you don't do domain acquisition, MPI. Right, with the overlapping computations how you do, but it's a GPU and then CPU and on different systems. It's interesting to answer that question. Okay. So for the quantum, you don't have the connection with the real quantum computer yet. You only on the simulator, right?
Right. But yeah, in next 6 or 8 months, we can have some real connection. Hopefully,
especially on the variational approach, right? That you can demonstrate that you can do large scale problem on Odyssey and the quantum computer that you have there. That would be very nice. Yeah, I think you are ahead of people.
So, and one of the expectation for the grasshopper is Grace is also a very strong CPU, and we can do some machine learning on the hopper part, and do some CSE simulation on Grace part. So it's possible.
Yeah. Yeah, because the demonstration that you do variational there, the optimization is very simple, right? You don't need the Odyssey to do optimization.
Okay.
Very nice. Thank you.
Thank you. So any other questions from audience? Okay. Okay, thank you very much for your attention. So let's go to the next.
Okay. Okay, so I'm Takashi Mukabe from the University of Tokyo. So as I'm talking about the fast prediction method for the steady flow simulation over the multiple domains. So this work is focused on the steady flow. Steady flow. And okay, so the computational fluid dynamics, so it's important application, the HPC. So since the CFD application are based on the many computation on a great measure of particle, as you know, so it is well known that the computation cost of the CFD is relatively high, and the CFD application require a lot of the computational time and the resources. So, okay. Recently the CFD has been used in the variety of fields, not just the example on the previous page. So CFD simulation are also used in steady flow simulation that do not change with time. So such as blood flow simulations. So, however, even if it is a steady flow simulation, since CFD requires large computational resources, so it is indispensable to accelerate the process of the CFD analysis. So in order to solve this problem, so we will use the deep learning to build a fast surrogate model for the approximating the steady flow simulations. So the challenge is here. So we are developing the deep learning surrogate for the steady flow simulations, and we are training the model on the multiple GPUs using the PyTorch, and we are predicting the flow around the complex shape. So we are also developing a prediction method using the deep learning with the boundary exchange for the steady flow simulation with the varying the size of the computational domain. Okay, so here is the basic idea of the deep neural network prediction of the flow. So first we perform the CFD simulation in the traditional way to generate the training data set. And in our research, we use the lattice-Boltzmann method for these simulations. And then once we have the data set, we build a neural network architecture based on the convolutional neural network in this case, and we train it. After training, so we can use the trained neural network to predict the CFD simulation results. So this is CNN may become the faster simulator. And so in our research, so we use the lattice-Boltzmann method to generate the all training data. And in this method, so instead of solving the Navier-Stokes equation directly, so fluid density on the lattice is simulated with the streaming and the collision processes. So since the distinct particle motion can be decomposed over the many processors, so efficient implementation on a parallel computer are relatively easy in this LBM case. So however, the LBMs still require many iterations to converge value or to achieve the desired result. So here is the data set for the training our neural network. So in order to make the training data set, so we perform the lattice-Boltzmann method simulation using the D2Q9 models with a random number of 20, because this is target is the steady flow. So the fluid flows along the x-axis, and we place the random size of the cylinders and the polygons at the random locations. So since it is difficult to train the model using the large size data, so we clip the data with the size of 256 times the 128 from the original data, and we split about the 60,000 data into the training data and the validation data. And we use the signed distance function to represent the geometry, so including the cylinders. So signed distance function, SDF, provides the universal representation for the different geometry shape and work efficiently with the neural network. And SDF provides the zero at the object surface, and the provides the positive distance in the fluid and the negative distance inside of the object. So the SDF is very often used to represent geometry in the conventional simulation as well. And here is the network architecture. So the encoding part is shared by the all dimensions, and the decoding part is different in each dimension. So the encoding part consists of the several convolution layers, and the decoding part consists of the several deconvolution layers. So we use the signed distance function as the boundary condition of the velocity as the input, and the signed distance function is used to represent the geometry. So this model provides the velocity field as the output. And in order to improve the accuracy, the model provides the information of the location of the object as mask. And here is the prediction result for the single domain case. So the left side of the figure is the CNN prediction of the velocity field. The middle figure shows the LBM ground truth. And the right side of the figure, the difference between the CNN prediction and the LBM result that the ground truth means. So that's shown in the figures. So our model will predict the LBM ground truth result and the result. And as I mentioned, so the training itself is done by the placing the simple shapes such as the cylinders and the polygons. But we can apply this network for the complex object. So here we show the result of the prediction for the complex for the row around the complex shapes that are not in the training data set. So on the left side is the prediction result by the CNN, and the middle side is the ground truth obtained by the LBM, and the right side is the difference between them. So that means the error. So we can see that the CNN prediction, the result with sufficient accuracy for the geometry that don't exist in the training data set. So the prediction time is, of course, very fast, and the LBM simulation takes 41.41 seconds for this case, even with using the GPU, while the CNN predicts result just in the 0.6 seconds. So CNN predict has achieved high accuracy with the significant reduction in the computational time. So then the next, in order to predict the result of the large size domain and flexibly handle input data of the various types, we've proposed the prediction method using a CNN with the boundary exchange. So in this method, we train the network model to predict the single domain result and apply it to the decomposed subdomains to predict the simulation result in each subdomain. So in order to maintain the consistency between the value in the subdomains, the boundary exchange between the neighbor subdomain is performed. So here is the detailed explanation of the performing the CNN and the boundary exchange. So the CNN predicts the value in each subdomain using the boundary value as input, and after that, updated boundary value are transferred to the neighbor subdomains, and the CNN and the boundary exchange are performed iteratively until the values converge. So we use the typical value of the LBM simulation as the unknown initial value of the boundary. So once the blue region is the predict, then the green region is the predict. So repeat this process. So here is the prediction result for the decomposed the multiple domains. So similar to the previous slides. So the left side of the left side of the figure the initial prediction, then by CNN and with the initial unknown boundary condition, and after the CNN boundary exchange between the subdomains are performed iteratively, the prediction value are converged to reach the final prediction in the middle panels. And the right side of the figure is the LBM, the ground truth. So as shown in this figure, so there is a little difference, but the development method can accurately predict the value in almost all the computational domains. So here is the detail of the conversion. Okay, so this graph shows the changing of the velocity in the x direction along the y-axis. So you can see that the value approaching the correct ones affected by the boundary value of each subdomain. And here the number is the iteration. I think this is the final step is 300. So wait a minute, and the video is may repeat. Okay. Here is the first initial value, and the boundary exchange transfers boundary exchange transfers the values on the boundary to the neighbor subdomains. So then we are, and after that, so that we can get the converged result right here, and that is already converged around 100 iterations. Okay. So here is the prediction result for the decomposed multiple domains with a complex shape that are not in the training data set. So the left side of the figure, the initial prediction by CNN with an initial unknown boundary condition. And after the CNN and boundary exchange between the subdomains performed iteratively, and the prediction value are converged to reach the final prediction is here. Here. And the right side of the figure is the LAVM, the ground truth, and this is the error between the difference between the LAVM ground truth and the CNN prediction result. So that's showing these figures. So although there is a little difference, especially in the boundary regions, the development method can accurately predict the value in almost all the computational domains. I mean, the error is about the 3%. Okay. So here is the most recent result from the joint research. So in the last this year, so in this study we have improved our original prediction method and apply it to the prediction of the blood flow simulation. So the red and the black box in the bottom figure is represent the subdomain. So in this study, we proposed the constrained CNN surrogate model. So the prediction of the blood flow means the prediction of the result of the simulation in a blood vessel. So that is the simulation has walls and not the periodic boundaries. So we set the boundary velocity value as 0, and the output is very different from the original one. So mass conservation is especially important in the blood flow simulation. So that the mean flow rate is utilized in the new surrogate model, and that rate is satisfied as the output of each subdomain. And here are the prediction result of the blood flow simulations. By adding the constraints, the simulation result predict with good accuracy. And also by utilizing the mean flow rate, the number of the iteration required to the converge is reduced. And in this simulation, so FEM was used to create the training dataset, not LBM. So that we have found that the proposed method can be used to predict the result of the simulation other than the LBM. So finally, I will show the difference in the prediction accuracy between the original data-driven method and the hard constrained method. So here, this table. So here is a global relative error between CNN and the FEM, the ground truth over the entire computational domain. So it can be seen that the new method is more accurate in its prediction. So because we are adding the constraint, physical constraint. Okay. And this is the final slide. The conclusion. So we have developed the deep learning fast precision method for the steady flow simulation. And we are predicting the LVM result by using the convolutional neural networks. And we are predicting the simulation result on the large size domain using a CNN with the boundary exchange method. So that means that this proposed method had no limitation for the device capacity. And also recently we proposed a new model with the hard constraint on the original proposed method, and it can predict the blood flow simulations. And the main point is that we are introduced the physical constraint and satisfy the mass conservation. And the future work that we will try to extend this method for the 3D simulation kit. And also we are considering adding other constraints. So thank you very much.
Thank you very much. Any questions or comments? I think it's very interesting that the thing that you do. I don't quite understand the whole. I don't understand the subdomain thing that you do. I don't understand the detail, of course, but I can read your paper later. But it's interesting that you train the CNN only on QA data driven, right?
Yes.
No.
The just only the original one is just only the CNN and the no physical constraint. So, but the new one, this one has the physical constraint because actually the first of all this research we have tried to apply the original method to this, but the result is not good. So we will decided to introduce a physical constraint.
Yeah, that's great. Thank you. So I think the domain very similar, right? You have the domain for the cylinder, the flow around the cylinder, and the flow around a car.
Yeah.
Yeah, square. Very rectangular.
Yeah.
The object are different. My question is that So you train one CNN for the flow over cylinder, and then you predict the solution for the flow over car. Is that correct? That's what you did?
Yeah, actually the wheel. Oh, okay, that's it. Come back. So the actual I have no the details. Yeah, here is the object type we use. So we use the polygon from the number variable from the 3 to 7, just only that, and also the cylinders.
Oh, okay. So maybe you have different object and.
Yes, maybe the very different object, but that is there is no card or no other kind of the complex shape in the training data set.
I see. So the car is one of the polygons. And see,
I mean that the how to say that we don't use that kind of shape in for the training data set, but not for but the point is that we use the signed distance function to represent that all the geometry. So maybe the convolutional neural network understands the distance from the surface. So maybe the CNN can predict the geometry. That is
right. But the CNNs, you have fixed input side, right? Image.
Yes.
CNN is all an image.
Yes. Right.
All rectangular.
Yeah.
So all the problem need to fit into like rectangular type of shape in order for the CNN to work, correct?
Yes, the input is the rectangle and yes. So the how to say that yes, and also the geometry is represented the kind of the group of the rectangle. How to say
But object is not rectangular. Let's say this.
yes, if you magnify that, you can see that the out of the squares. Yes.
So the domain, I'm talking about the domain. The domain is rectangular, right?
Right.
Let's now I'm looking for the simulation with the domain like this.
Yes.
It's no longer rectangular.
Yeah.
Can you use your train CNN predict the solution on non-rectangular domain? Not object, the domain.
Domain. No. The all rectangular is a computational domain. So I didn't try to apply this not to the rectangular domain.
Yeah, because CNN require
yes.
Size, right? Okay.
Yes. So in this case, the 256 times 128. Yes.
Thank you. Great work.
Thank you very much.
There's a question there.
The question is, can we make the CNN to run the difference between the ground truth and the prediction bars? Can we CNN to run the answer is maybe yes. So I actually I could. But of course, but the little difference, and also in this case, as I said, this is the steady flow simulation. So if of course we want to predict the time dependent flow. So in that case, it is very difficult. So and that is maybe the future work. So we will try to do that.
One more question. Why lattice? Why lattice Boltzmann method? Why not, CFD like finite element or other finite different? Why lattice?
Actually, my work is focused on the GPU computing originally. So as you know, the lattice-Boltzmann method is suited for the GPU computation because it is just uses the structure mesh. So we can accelerate the LBM using the GPU can accelerate the LBM method.
You can do it for one element and other method as well, right?
Yes, but the finite element method is requires a Poisson solver.
Oh, it depends.
If for example in this case,
Incompressible, you
yeah,
incompressible dynamics.
yes, in this case. Oh, so yes, that is the explicit method. The LBM is one of the explicit, so that we don't have to solve the Poisson equation. So that means that we can easily to perform the large scale simulations.
Yeah, well, yeah, I see. But depend on the method. What
Yeah,
depend on the method?
Yeah,
Because if you use if you look at incompressible.
yes, the compressed flow case is you of course it is not required to solve the Poisson equation, so that is okay. But in compressed flow case, the LBM is usually used for the incompressed case. So but this is we don't have to solve the Poisson equation.
Yeah.
That is
I mean is that their finite element method solving incompressible flow without solving the Poisson equation, right? Sorry. Poisson equation.
Yeah.
There are just mentioned. Okay, good. Thank you.
Okay, any other questions?
Thank you.
Okay, so thank you very much for joining us.
Ask the question. I have questions. In the Zoom.
Zoom have a question.
これもうさっき今答えで、はい、大丈夫です。Yeah, already answered. Okay, thank you.
Okay, so thank you very much for joining us for the Friday afternoon. So I hope all of you enjoyed the conference and talk. So currently, I have no plan for the next one. Yeah, we make some announcement. Yeah, we have some update. Okay, so thank you very much again.
Thank
And
you.
have a nice weekend. Thank you.